All right, welcome to the final unit of this week about sequences. Okay, so what is a sequence? Well, a sequence is a list of objects, okay, sometimes called terms or components or elements. And we denote these either by with parentheses or with these triangular brackets. Okay, so for example, here A, comma B, comma C, comma dot 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 dot. This represents some sequence of these values. More examples. Suppose, for example, if you've heard, the Fibonacci number sequence. So this is a sequence, actually it's very cool, it has a lot of different things related to it. This came about back in the 1200s in Italy, but actually there's been evidence that it's, came about even many years before that in India. In fact, I remember in grade school once we were given the sequence of numbers on the chalkboard and told to try to figure out what's the pattern. And given enough time, we did figure out what the pattern is. So, if you want to, you can pause the video and try to figure out the pattern. Not so important for this lecture. But this is defined by starting with 0 and 1, and then each further number is defined by taking the sum of the previous two. So what am I getting at with all these examples, and how does this compare to what we've seen just up till now about sets? Okay, so there's a few key differences between a set and a sequence. The first is that in a sequence, elements are not required to be distinct. Okay, so even here in this previous Fibonacci example, I have 0, 1, 1. And these are two instances of 1. I can't just squash those down like we did with sets. Okay, so here I have, maybe this example is a good indication here. So for example, as a sequence, which you can tell because it's going to be in the parentheses or triangular brackets, something like A, comma B, comma A is a sequence of 3 elements. But as soon as you put curly braces around this thing, that tells you this is a set. And here for a set, you're either in the set or not in the set, and there's no notion of multiple copies in a set. Okay, so here A, comma B, comma A in the curly braces is a set of 2 elements. Okay, the other big difference is that the terms in a sequence have a specified order. The order matters. Okay, so for example, the Fibonacci sequence as it is, if I decide to move some of the numbers and swap places, it's a different sequence. Versus if we were just talking about sets, if I have like the set of A, B, C and the set of C, B, A, these are the same things. It's a different object, sort of a different data type you can think of, where you don't have a notion of ordering or copies for sets and you do for sequences. Okay, so a special case that you've probably seen all over the place of sequences are short sequences of pairs, ordered pairs. Okay, so notationally this will be something like A, comma B in parentheses. And the functional definition here, so when we define these new objects, I defined to you before what is, how are sets defined and when are 2 sets equal. Here you have an analogous sort of definition and you have a different notion of when are 2 sequences equal. Okay, so in this case, if I'm looking just at ordered pairs, 2 ordered pairs, A, B, and C, D, are equal if and only if each of the individual elements are equal. That is, A is equal to C and B is equal to D. Okay, so this down here is indeed for the curious only. And even like, what do I mean here is a good question. So I claim that suppose that I only give you the structure of sets. And now you somehow want to use these, you want to build on top of sets to define something that satisfies the property of sequences. Okay, so for example, how can I define A, comma B, the ordered pair, if all I'm giving you to define these things are sets? So you can't just define it as the set A, comma B, because then if I have A, comma B is the same as B, comma A, for example. Okay, so here with this for the curious only, is giving a way that you can define and you can actually emulate the structure, the extra structure of sequences by only using sets. So for example, if I want to define A comma B, as I said, I can't just take A comma B as a set, but what I can do is define a set that has just A, okay, and then also A comma B. These are elements of that set. And loosely, I'm not going to prove anything. In fact, we'll talk about it next semester. But loosely, this gives you some way of distinguishing which was the first of the two elements. Okay, so this already separates now A comma B from B comma A. Okay, so this was ordered pairs. And of course, it doesn't stop there. In general, you can extend this to define ordered triples, ordered quadruples, it keeps going, to ordered n tuples. So here I've got n elements in the sequence. And in fact, even it doesn't necessarily stop there. This also we'll mostly talk about next semester, but you can even consider infinite sequences. So a really useful tool, this is going to be maybe not so much a tool, but a definition, is the Cartesian product of two sets. So here, if I start with a set A and a set B, the Cartesian product of these sets, A cross B, is equal to a new set, okay, where the elements of the new set are going to be ordered pairs. Okay, so take a look, for example, at this set builder notation line. A cross B, this is the product, the Cartesian product of the two sets, is equal to all of the ordered pairs little a comma little b, such that I go over all the different options of little a coming from big A, and all the different options of little b coming from big B. Okay? And note here, in particular, that the order of A and B does matter. You'll get sequences in the opposite order if you do it B cross A. Okay, so what's an example of this product? Okay, so say that my first set contains the elements 1 and 2, and my second set contains the elements 1 and 3. What will be my resulting Cartesian product of these sets? Okay, and let me pause for one moment here and give you one useful clue. Okay, so remember we had some tricks, say when you're computing the power set, how many elements do you expect to be there in the power set? Remember that's 2 to the elements of the original set. Now in this case, if I have a set of, say, n elements and a set of m elements, how many different elements will be in the Cartesian product? Well, it's going to be the size of A times the size of B. And why is that? Because, okay, so think about it, all of these ordered pairs. Suppose I listed out all of the ordered pairs in A cross B. Then in the first position, I have all the different elements of A that I can scroll through, okay? And for each of those, I have all the possible options for elements of B. Okay, so I get size of A times the size of B, many elements. So in particular here, for example, if these were my example sets, I have 2 elements in A, 2 elements in B, so I expect 4 elements in their product. And indeed, I have 1, 1, 1, 3, 2, 1, and 2, 3. So I went through the elements of A one by one, and then paired them up with elements of B one by one. Okay, so that was the Cartesian product of two sets, and it certainly also doesn't need to stop there. You can consider the product of many sets. So here, say S1 cross S2 cross ... cross Sn. This is again a new set. Okay, but what are the elements of this new set? So before we had 2 sets and we got ordered pairs. Now I have n sets, and my elements will be ordered n tuples. Okay, but other than that, it's exactly the same game, where all of my first elements are coming from the first set, second elements from second set, and so forth. Okay, and set builder notation here, for example, if I have S1 cross ... cross Sn, this is the set of all of these ordered n tuples, little s1 up to Sn, such that S1 comes from big S1, S2 comes from big S2, and so forth. Okay. So what about this? Here I have a set that's not finite. I'm taking the product of all the natural numbers cross the set A comma B. Okay, so here, of course, now how many elements does this set have? Well, it's going to be infinite. Maybe that doesn't help so much. But what will it look like? It'll look like, again, kind of going through all the elements of the natural numbers and pairing it. So I have 0A, 0B, 1A, 1B, 2A, 2B, and so forth. Okay. One notational point here. So if you ever see the notation of a set raised to a power, what this means, what this denotes, is that you're taking that set and taking the Cartesian product of that set with itself n many times. Okay, so for example, suppose that you see the set 0, 1 raised to the 3. What is that? Okay, well this means 0, 1 cross 0, 1 cross 0, 1. I've got it 3 times. And how many, tell me about this thing. How many elements should this have? What should the elements look like? Okay. Well, first of all, because I have the set cross the set cross the set, I've got 3 sets that I'm taking across this Cartesian product of. The elements of the resulting set will be 3 tuples. Okay. And now, how many elements will it have? Well, I have so it was 0, 1 cross 0, 1 cross 0, 1. I had 2 options for the first component. For each of those, I have 2 options for the second. And for each of both of those, I have 2 options for the third. Okay, so I'm going to have 2 to the 3 or 8 different elements. And if you go through all the options, they're listed here. All right, so let's briefly recap what we saw all together today. In the first part, we went more and talked about sets, starting with set builder notation. Remember here, this is the notation with the curly braces, starting on the left with elements X coming from some larger set. Karate chop, predicate on the right. And this describes the set of all elements that satisfy that predicate. We talked about Venn diagrams and how to use them as a useful tool for giving you intuition and sort of leading you toward a proof of a statement regarding sets. We talked about the symmetric difference just now. Remember, this is the set that's sort of combined with these 2 pieces. All of those, the symmetric difference of X and Y, contains all the elements that are in exactly one of those 2 sets, but not both. And I highly recommend, highly recommend you take a look at the glossary of terms on one of the previous slides. And you can go through and test yourself and make sure that you're well understood with each of those. Okay, then at the very end, we had one unit just now about sequences. And here the big difference between sets and sequences is that for sequences, the order matters and you can have repetitions. So for example, I can have 1, 1, 1, 2, 1, and that's a perfectly good sequence. Versus if this were a set, I would lose the order and I'd lose the fact that you have multiple copies of 1. Okay, and notationally, an important point is that sets use these curly braces, and sequences will use either parentheses or triangular brackets. Okay, so this is your clue, both to when you see something, you'll automatically know this is a set or this is a sequence. And in reverse, when you're trying to describe something, this is how you can communicate to others what the type is. Okay, and finally at the end, we just talked about Cartesian product of sets. Okay, so A cross B or A cross B cross C cross, however many you like. And a reminder that the notation, if you see a set raised to an exponent, this is the operation that they're talking about. So for example, A cubed, that really means A cross A cross A cross A 3 times. Okay, so this is the end of this week, and see you next week. We'll be talking about functions.